Yeah, hello everyone. I am Yash or Popular Plus Plus, and let's start with the discussion of today's topics, which are like binary lifting, and with that LC. Okay, so I will be referring to one of the problems of food chef. Let me share my screen. Is my screen visible? Can anyone just tell me if my screen is visible? Yeah. Okay. Thank you. So here's the problem. So it says that you are given an array of size n and a segment is called good if it can be divided into at most k segments, so that each segment has some at most s. Okay, and here are the constraints. So you can see that n square would n or nk would not work over here. Okay, so let's go on to the approach we would first think of. So basically it says that there is some array A2 and AN, and here it says that you have to choose some segment. Let me say that segment be AL to AR. Okay, and now you divide this continuous sub segment into K segments. So the sum is at most K. So of course greedily what will be optimal is, for if you have some AL, then you will keep adding AL plus 1 up till AR1 such that sum is less than S. Okay, and once you can't take AR plus 1, you will start a new segment, right? And this you have to do K times. So you are repeating same thing K times, correct? Of taking the sum, and it's a continuous segment. So if you do it with brute force, it's NK, which won't work, which is quite slow over here. Okay, so we need to do this in parts. So what do we do is, for each I we calculate next j such that this is a segment at most sum with some at most s, right? So this is for 0. Now similarly we, for each I we calculate answer for I comma 2 to the power 0, I to 2 to the power 1. So basically your starting index is I and your k is 2 to the power 0, 2 to the power 1, and similarly I and 2 to the power b. Okay, for some integer b, for some number b. Okay, so you do this, and this I is from 1 to n. Okay, so basically for each integer you are calculating the answer when the k is 2 to the power something. Okay, so once you get this, you can get the answer, because k can be represented in some bits of zeros, ones, right? So when you are if you want to start from position I, where L is I, okay. So you can see that this bit is present, right? So you can get the answer of I to I plus 2 to the power whatever is j, and your next time when you take some bit, you need to start from I plus 2 to the power j. So this is inclusive, and then next time you start from this position, right? So that's how you can continue, as it's a continuous segment, and you can divide k into power of bits, right? So this is how, using this pre-calculations, you can find the answer for some particular k with different number of bits to the power bits, right? So now the thing is, we need to optimally find for each I 2 to the power 0, I to, let us say, function of I comma 2 0. Basically this is position of starting position, this is k. So this comma f I comma 2 to the power 1, and we need to pre-calculate this and we need to recalculate up to fi comma 2 to the power b. Okay, and the maximum bit of k can be around 20. Let's keep 20 on the safer side. So b can be something like 25 or something. It depends, like, to be safe. Okay, so this is what we need to do, right? So now how do we calculate this optimally, right? Because brute force will again exceed the time limit. So how to do that? So here we use the commonly used technique which is known as binary lifting. As you can see, these are binary length, and you can do something using this binary thing. So basically, first we calculate answer for or f of I comma 2 to the power 0 for all I. Okay. So once you have calculated this can be calculated like using two methods. Okay. So first, let's see how to calculate this. Two methods are binary search and two pointer method. Okay, we need to calculate for each. So I would be showing you the binary search method, but two pointer would be more easier and more faster to implement. So it's always optimal to like here it's optimal to use two pointer method, and where it's like a quite basic two pointer method where you keep I and j. I keeps going ahead, and once you have sum greater than s for all the j's, after removing that j as well, the sum is greater than s. You need to uh, like point that j should point at I, and when the sum is again less than s, you can continue, and for all j's other than like when I ends, you can point as n, because we if this gives us the position, first position which is not included starting from I, right? So suppose it's like f of I comma 2 to the power 0 gives I plus 5. That means it includes I plus 1 till I plus 4. The range is 5, and the next element from which we need to start is I plus 5. Okay, so this is what we get from two pointer. And for binary search method, what you can do is you actually you can use your normal binary search. You can type it on your own, and that's I guess quite easy. But if you want to use lower bound or upper one, whatever, yeah. So what you can do is you can use prefix sum. So basically you calculate or p1, p2 up till pn, and for each I you need to find the first prefix sum, like p of I minus 1 plus s. You need to find the first position j, which is equal to like which has some which has p. You need to first find j which has pj equals to p of I minus 1 over, yeah, p of I minus 1 plus s, like including I till something like that gives the sum. It's like the previous sum, and plus s is the max sum you can get from I to some position j. So this is how you can get using binary search the first position. So for the initial condition of I and 2 comma 0, you can get it in log n in total, right? So now you got this base, but when the k increases to 2 to the power 5 to the power 10, how can you do it, right? So we will use the previous bit answers and the property that 2 to 2, yeah, 2 to the power j is nothing but 2 to the power j minus 1 plus 2 to the power j minus 1. You just take 2 power j minus 1 common, 1 plus 1 which is 2, and if you multiply you get 2 to the power j. Okay, so we will use this property to find all the other answers. So what we will do is, now for f of I comma 2 to the power 1 is nothing but f of I 2 to the power 0 comma 2 to the power 0. So basically, what does f of I comma 2 to the power 0 give me? The first element j, which from I is cannot be taken in the segment, like the sum exceeds when we take this j, right? So this will give me that j, and from this j I need to find this 2 to the power 0, because I have already taken one segment and 2 to the power 1 is nothing but 2, so I only need to take one more segment, right? So this is the recursive formula for binary lifting, and when you lift each bit, you use the previous bit to find the answer. So this will give me f of I comma 2 to the power 1, which will point to the j such that that j cannot be included in the substring of s when k is equals to 2. Yeah, k is equals to 2 to the power 1, which is 2, right? Similarly, for you can say like f of 2 I comma 2 to the power 2 is nothing but f of I comma 2 to the power 1 comma 2 to the power 1, right? So this again give me j, which I got over here, like taking two segments, and from that j I need to find taking two segments again. So it's like for going all the bits from lower bits to upper bits, and we find all answer for all the bits for each, like for each bit we find answer for all elements, and then we go to the next bit, and then we can decompose k into such bits and find the maximum when we start from each I. So basically, query process is like when you start at I, you find the bits of k, and if that is set, then you take f of I comma 2 to the power b for that bit, and this keeps on going, and you get finally the j, which is not included, and then the answer if you start at I will be j minus I, correct? And you need to maximize this j minus I. That's all. So overall, this can be solved like the initial part is order of n log n, as for each one you need to pre-compute, it's only order of, like, for each log n of bits it's only order of n, because the function here is nothing but order of one function, because this is already pre-calculated, right? And f of this comma this is also already pre-calculated, so it's order of 1, and we have order of n log n for that upper bound thing, and if you use two pointers then it's again order of n, so we'll keep that order of n, and the query part is solved in order of q log n again, and this log k, log k, because we are taking the bits of k, right? So for each k, oh no, queries are also solved in order of n, there is no q. Q is nothing but n, because there are n positions, so it's again n log k, right? So overall complexity comes to order of n log k. Is it clear to everyone? Does anyone has doubt? Okay. Yeah, then I'll proceed to the code. Yeah, so here's the code. Basically, this is nothing but taking the input, and this is nothing but the prefix sum. This is the binary exponential. So here L, that is the B is only till 17, uh, because it's like very cut to cut. You should like take 20, 25. Doesn't matter much. So this is the array, and we here find f of I comma 0 for each I. Basically I comma 0, right? And using upper bound, and I as a 3 years, yeah, this is nothing but prefix till I minus 1 plus s, because we are removing the current element from the prefix as. I hope everyone is aware with prefix sum. It's nothing but sum, taking sum of all array, and for range sum you remove the sum till the L minus 1 element. and take the sum till r. Okay. And this is how we calculate the first element of the binary exponentiation. Then we use the recursive function, same as explained. And then for each bit, for each element, if we start at this element, then we need to calculate if that bit is present, and if it's present, then this increase the I, that is valid current, like last j is nothing but the j, and just increase the j to some element, and then find the answer and just print it, and it gives easy. Yeah, that was the code. Yeah. Any doubts in the code? Mm, okay. Then we can move to the next problem, which is company queries one. The boss has basically you're given a tree with a rooted node, and you need to process Q queries like who is the boss of X at the K levels up in the hierarchy. So basically, you are given a tree, right? So rooted tree you are given, and for each node, let me say for this node, you need to find the kth boss. Okay, so suppose k is 2, so kth boss of kth boss of this node will be 1 and 2, which is this. Basically finding the kth node from the path from u to the root. Okay, so here this node, this node, this node, this node, this like this is 1, 2, 3, 4, right? And like this you're doing k and you're doing q queries, right? So again, thing is this k can be, we can use binary lifting over here because there aren't any good other ways. Like they are all difficult ways, other ways to find. This is the easiest way. You can't use binary search over here because whenever you find mid, you need to find who is the middle ancestor, which is again not possible, right? So it's like tough with or I guess not possible with binary search. So you need to do binary lifting. Again, similar thing. This for each key can be composed in bits, right? Similarly, and we can find going this bits up. But the thing is, in the previous problem, we had like there are some edges. We can also convert the previous problem in some graph type. Like there was some edge from I to J, something like that, where this is a segment. Therefore, I minus 1 there was edge to some J1. That was a segment, right? These were the edges. Here, just the edges are not in like a line format. Okay, so for for us to do binary lifting over here, we need to just focus on the parent because we need to go only up from this node. We need to go to the root node to find the kth boss. Okay, so we need to only go up. So what do we do is again we like do a normal DFS. So let's start from the root node. Okay, and you for root node we find all the functions, right? So for f of root comma 2 to the power b is solved for all b is from like 0 to 20, all b it's solved. Okay, and then we proceed the DFS to its children for this. Then we solve for all b, we solve for this. Then we go on back to root. Then again we come here, solve for everything for this, and then we go to its children. Because for these children, we always take these nodes, right? So for these nodes should be completely done. And similarly for this node, we only use the root node. So root node should be completely pre-calculated. Similarly for this node, we use these three nodes. So So these three nodes, answer should be pre-calculated, right? And what is the pre-calculation formula? Is just like up of, let me say, function up of node comma mask. Okay, this is nothing but mask. So let me say 2 to the power mask. It will be easy. It's nothing but again up of node comma 2 to the power mask minus 1. Okay, so this gives me the node of up comma node to mask minus 1, and that parent to mask minus 1. So it's the same thing we are doing, same recursive formula, right? To find this, and of course up of, and we know that up of node comma 0 is nothing but parent, right? Because first pause, right? So that's the recursive formula for this problem on binary lifting on trees. So does anyone has any doubt? Or should I continue? Yeah, there is. You can find NC in order of one as well, but that's not like necessary generally in the problem. You like generally order of log n works fine, and that's like a little complex. So we can go on to solution, I assume. So here is the thing. Actually, don't need this part. I am not going to evidence tool, but just assume this up. Or actually, no, this don't need this timer. So basically, up of node of 0 is parent, and for I to all the bits, up of I, if it's not minus 1, because here we need to print minus 1 if they are more than k, if like k is more than all the bosses up there. So if it's minus 1, then it will give me a runtime error, which I was getting actually. So you just keep this as well as minus 1. Else you keep it as you have this node and you do the same thing, recursion, and here you give parent node and parent. You get parent in function, and then after DFS you can just for each query go for L minus 1 to for each bit, and if it's check if the bit is present in K, then go up that much to the power I, okay? And then print the U. This gives easy, works quite well. Other ways to keep other than other ways, like, then I don't think there are, but at the end you use like the binary lifting, because in binary search again you search but you need binary lifting. You can, yeah, actually if there are, then there will be like too much complex. Actually, when you use binary search, so what will you binary search? You like binary search in distance, right? And distance again needs binary lifting. Or if you binary search on nodes, you can't actually binary search on nodes because it's like a tree. So suppose you have like just you have like a tree, right? So if it's something like this is 1, this is 2, this is 3. So actually for 4, 3 is not in the path from to the root, right? So actually you can't binary you can binary search on these node indices. You need to binary search on the distance again, and again for some distance you need to find the which node is there with that distance x, and it's again binary lifting. And other methods, there might be very complex methods, I don't know, but yeah, why to use so much complex? So now let's go on to the next thing. So first, let's go on a brief explanation of Euler's tour. So we need LCA for that, right? Let's read the problem first. Let's read. Yeah, this is the problem. It's company queries 2. Yeah. So it's nothing but in each query this time you are given two employees A and B, and you need to find who is the lowest common boss of those employees. Okay. So yeah. So basically you are again given a tree. Such a bad tree. Okay, something like this, and then you are given two nodes. Let's suppose you are given nodes U and V. Okay, and you need to find the lowest common ancestor. So like they are asking is from the path from U to the root and from the path from V to the root, you need to find the first node which they both have in common, which is nothing but the lowest common ancestor. So you will go this, and for this is nothing but this and this. So this node is the node in common, right? So this is our final answer is this node. Right. So how do you calculate this? Using binary lifting, right? Because LC using binary lifting. So what you do is you need to find like some way so that you know that this node and this node both are like in the subtree of the same node, right? Because this node, uh, yeah, this node if you check, then this is not in the subtree. Only this is in the subtree, right? But for this node, we know that both this and this node are in the subtree. Or suppose, like for this node also, as it can be the node itself. Only this is in the subtree, not this node, right? So you need the first node that both the other nodes whose LCA we are finding are in its subtree, right? Only then it will be the lowest common ancestor. Else it won't be the lowest common ancestor, right? So we need to find this first node. But how to check if some node is in the subtree of the node or not? So hereby we need Euler's tool. So basically how it works is you get the entry time of each node, let's say T in for each node, and you get the exit time of each node. So it's T out of each node, right? So when you loop in the DFS, you can just have an example, and this helps. Is used widely for converting the tree into an array, so that you can use segment trees on that and stuff. So it's quite useful in advanced topic as well. This is the most basic topic where this is used, and there are various types of tools. So only entry time, only exit time, and with different needs. We will be using both entry and exit time over here. So it is like first you go to root. So teen of root. Let me say. Let me decrease the size of tree. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Let me say this is the order. And blue represents entry time and green represents exit. So entry time for node 1 is 0. Then it goes to node 2. So entry time becomes 1. Every time you visit a node or you go out of the node, like each entry time is unique for all nodes. So only one entry time, only one node at that point. Okay. From 2 you go to 3. So it's entry time 2. Now you go back to 2, right? So it's exit time as well. So it's like exit time 3 because you are going back. Every time is like an index and only one node can have that time. So it's like that, and then you go to 2 back and again you go to 4, right? So you are not exiting to 8. So it won't be exit time there, and it will be 4 over here, the entry time of 4, and again you exit this, so it's 5, right? Because you're exiting. Now you go to 2 again, then you again go to 5, where you have 6 as the entry time, and again you go out of 5, so 7. And now you are never going to visit 2 again, right? So you are exiting 2. So 2 will have the exit time 8, and then you go to 1, and then you visit 6. So 6 has entry time 9, and then 6 has exit time 10, then 7 has entry time 11, 8 has entry time 12, 8 has exit time 13, 7 has exit time 14, 1 has exit time 15. Okay, so these are the exit time and entry times of each node. So now what is the property used so that we can determine if the node X is in the subtree of node Y or vice versa. So the thing here is you can observe that one has the least entry time and the largest exit time. And for 2, it's like entry time is lower, exit time is not the largest but quite large. And you can see that all the nodes in 2 have entry time more than what 2 has, because of course 2 will be entered previous before any other node in its subtree, right? So its entry time is the least, right? These are high, this is the least, and the exit time of 2 is greater than the exit time of all the other children in its subtree, right? Because it's exited at the last. First, all the children in its subtree are exited, and only then 2 can be exited, right? So this gives us the condition that if some node is in the subtree, then it's teen. Suppose X is parent and Y is child. Then you know that teen T in of parent is less than T in of child, and T out of parent is greater than T out of child. Okay, these both conditions are satisfied, then we know that the T is the parent and C is the child. But if both are not satisfied, suppose if only T in is satisfied, okay, T out is not satisfied. See, we can have nodes something like 2 and 6, because here T in is less, but T out is also less than 10, right? Or if only T out is satisfied, then we have 6 and 2, because T in is greater and T out is less. So both the conditions need to be satisfied. Then we know that P is the parent and C is the child. Else it's not the case. Okay. So this is how we using ELO's tool find out how to get the whether we know them. So now let's come back to the problem. So yeah, here we have two nodes A and B, and you need to find this node, right? So what we do is we find this node and we find this node. What are these nodes? Basically, these are the two nodes after which if we go about parent of this and parent of this, we will get the least common ancestor, right? So what we do is we use binary lifting over here, and for each node we have already calculated, like in the previous problem we know how to calculate the parent at the kth distance, right? So here what we do is we know that this distance to this node distance is some k value k, right? And this k can again be represented in bits. So here we go is we go to the, like, if we try taking the to the power ith parent as in one of the bit in k, and if it's in this range, okay, then it will give me that this other node, suppose you are starting and only focusing on this node, then this other node will have it, like these both nodes will have this other node in its subtree as well, and this checking can be done in order of one using this t of time, right? So this is how we know. But if we have some nodes in this region which does not have this in its child, then we know that we can go to this node, right? Because that node is not the LCA. So similarly, we keep going up, we keep going up, we keep going up until the node says that the next node is LCA. Because we if we by chance had come to this node checking, like we would have, and we will check that this is yes, so it surely gives me that yes, it is in the, it's a child, then we don't take. So basically we are only taking these nodes, and then the next node we know surely is the LC, right? So this is how we use binary lifting. And so, but here there are corner cases as well. Okay, so let's go on to that corner cases. The two corner cases, like both the similar one. The corner cases are, this is A and this is B, right? So here we like directly give that this is the LCA using T in T out time. We cannot directly give because we find that this is also in this subtree and this is also in its subtree, right? But the thing is, here LCA might not work because if we choose the one of the nodes as the LCA itself, then how it will work? That's the thing. If we choose as this as well, still like it's not. There's a possibility we choose this one, right? And if we choose this one, then this will actually be in separate. So it will be a vice versa case. So we don't want to go in that complexity. And the other cases like the same thing. This can be x and this can be y, or this can be y and this can be x. So we need to check both ways. And if it's already in like this condition, then the LC is a thing with this node, right? According to the definition. So this is how we find LCA. Does anyone has any doubt? Binary search, we can actually, yeah, we can do use binary search, but that will be order of n log square n, because for each binary search you again do binary lifting, right, to find the kth person in this. So that's the thing, that's a bad time complexity than by just binary lifting, right? So we are discussing company queries too. As into zero. Yeah, so I will go to the code now. Company queries 2. Oh, yeah, this someone was asking about order of 1 LCA. This is the one using sparse table. But yeah, I'm not going into that now. I can go in the next lecture probably in the advanced one. So this is how we write LC, like at least I write LC. You can find similar stuff in CPP algorithms, like I learned from there. So here we need actually time, T in time and T out time of each node. But in DFS, you similarly you just do pre-calculation binary lifting over here, and you just do DFS, and you have this T in time when you enter and T out time when you leave the function. Is ancestor gives you whether u is the ancestor of v. I've used less than equal to because if u and v are the same, still the u is the ancestor of v, right? Because it's the same, we still count it in the ancestor. So that's why like it's counted in this subtree. So that's why u is greater than equal to, and this is how we calculate LCA. Is u ancestor, is v ancestor, else we like one of the node is u, and we keep finding the node so that that is not the ancestor of v, and if it's not, then we can go up to that node, and of course we go from the greatest bit to the lowest bit, because like if you go the lowest from the lowest bit, then you can't, that's not logical. Just try doing that and you will get it. Yeah, and this is how you get a and b, just find LC of a and b. That's it. Yeah, that was company queries 2. Now let's in LCA itself. Let's see some harder problems. Okay, this was straightforward LCA. The next problem is mm, yet another palindromic problem. So I'm gonna you retrieve it in notes. Each node is assigned a alphabet. Find the LCA and distance is from A to B excluding B. Q queries, and if the subsequence of this and a non-empty subsequent of each of that, it is a palindrome. Concentration of this. Okay. Again, the inputs are large, so it's like LCA. It's like directly saying you to calculate LCA. Okay, and so you need to binary lifting. You need binary lifting and finding LCA. But what else does this problem see? Palindrome and subsequence and stuff. So yeah, palindrome. So palindrome is nothing but write the same front from the front, like, and backward. It's read the same. So A, then the back should be A. If it's B, then it's B. If it's A again, then it's A, C, C, A. So you can see that A, B, A, C, A, C, A, B, A, and A, B, A, C, A, C, A, B, A. It's read the same. This is nothing but palindrome. And subsequences like it's like A, B, A, C, A, C, A, B, D. So take this, this, this. It's like A, B, A, B, D. It's not continuous. It's like some random element, but in order of how they appear. So here they say that they are given some tree, okay, and each node is assigned a character, right? And you are given two queries, and each query you are given two nodes, let's say U and V, and you find the LCA of those, and then path from U to LCA excluding the LCA, and path from V to LCA excluding the LCA. Okay, it forms some string, right? So if you take the characters, then BA. So first string is BA, second string is AB, right? So now you merge these into no, like you have this and this. Now you choose some subsequence of this string S1 and string S2. Let me say I choose subsequence as B. So S1 is B, S2 I find choose subsequence B. Okay, but it's the second one. S2 is also B. So S1 plus S2 should be a palindrome, which is BB, which is again a palindrome. And size should be greater than 1. Size should not be 1. Else, like it's very. Yeah, both from both the elements you should choose at least one. So size will be 2 or greater than 2. As S1 will have at least one size and S2 will have at least one size. Okay. And you just need to tell if a palindrome exists or not. Okay. Here you can also choose B and AB. Merging is BAAB, which is also palindrome. But here they have not asked for the longest size of the palindrome. They have just asked to check if a palindrome exists or not. Okay, so what comes in the mind is like why to take big palindromes? You can take small palindromes because if A B A is a palindrome, then like this is a palindrome, then A or let me say C A B A C is also a palindrome. So we remove this C, we remove this C, we come to this A B A, and I know that A B A is a palindrome, then A is also a palindrome, right? So why to take this middle one? Because it's a subsequence. So I just take one element from S1, one element from S2, and I get a palindrome, right? So it's like taking same character from S1 and S2 to get a palindrome, which is you come to down to the problem that from U to LCA excluding LCA. Okay, so basically U to LCA, U comma V, and V to LCA u comma v. Okay, this nodes and these nodes in this path should have at least one character common, right? So there are at most 26 characters. For each character, you need to find if it is present in this range and it is present in this range. How do you do that? So basically, this is a continuous range, right? So we can use prefix sum on trees. So what is that is you know how to calculate the frequency like a prefix sum of each character. Basically, for each character, there are 26 prefix sums, right? And of size n. And for each one, basically, in an array, what you do is you have given a string s, right? So, how do you calculate prefix sum on this s for each character? Take the previous character, if the current character is also there, increase the prefix sum by 1. That means one more character is present over here. And you find number of characters from range L to R using this same prefix sum formula PR minus PL minus 1, right? But in trees, what you do is it's the same thing as we changed in binary lifting. Like the edge is to the parent, right? So it's same thing, just we do prefix sum with the parent. So there is a P of C comma C is the child, or let me say V comma character is nothing but P of u comma character, how many characters in the parent, plus if if s of v is c. Basically, if this one is also a character, then you increment by one, else you don't increment and you choose the parent, right? And here this comes to the case that for each character we just need to find if we need to find p of u comma c minus p of lc. Okay, we are excluding lc, so it's like lc comma, right? This will give me if so that the frequency of that character in the path, this path, in this path, right? And if it's present, then this will be greater than 0, and same we do for this one. And if both are greater than 0, that means for some that character c, you can have it in a subsequence of both the elements, and answer is yes, else the answer is no. Okay, any doubts? So let's go on to the code then. Basically, it's the same thing, teen time, no up, and the binary lifting. And this is nothing but the prefix sum. So pre of node of I is nothing but the character 10 to 25. Is nothing but pre of parent of I, and for this current character, for this one, it's zero listing stuff. So we increase the frequency and then we do the DFS and then P out time. This is LC or is ancestor. What need is, and final CA is the same thing as we did in that company queries too. And then this is the simplest prefix sums, initialization. And then for each query you have UV, find LC of U and V, answer is currently no. And for each character you find you have no LC, right? So you find pre of UI minus LCA and Y is pre of VI minus LCA, both are greater than 0, answer is yes. And then print answer and then clear the distance. The order is q times when log n. This is also log n. This is also log n. Nearly log n or 26 and log n. And this is also n into 26. This is n into 26 plus log n. And this is again okay. This is okay. Yeah, and it gives correct. And that was this problem. Does anyone have any doubt? Uh, this is for the day. I will be sharing more problems soon. and I will be having an advanced, the next lecture, where I will be discussing some or probably all of the problems, and if possible, then I will also explain the thing ask order of one LCA. I will also explain that if possible. Yeah. Thanks everyone for attending the lecture. Hope you understood the concept. Yeah. Okay, let's see the next lecture. Thank you.